This week we're going to be focusing on shoreline processes. So what are our objectives today? We're going to focus on what are tides. Number 2, we're going to be looking at elements of waves. And then 3, we're going to get into the effects of wave erosion. And number 4, we're going to kind of briefly introduce what is the definition of like wave refraction and longshore transport. And then finally, we'll be getting into erosional and depositional landforms of coastlines. And then lastly, how does human activity influence shorelines? And I will talk about different types of mitigations, how we can engineer different structures that help reduce erosional processes. So here's this slide just basically showing you basically what coastal environments look like. This is kind of just a 3D model showing where a beach environment would occur here. It's showing also here landward where we have basically mountainous terrain, where we have river systems that are that emanate from high elevations and flow towards the ocean. We also have delta complexes that form that enter a large body of water here. And then as we move out oceanward, we get into these submarine trenches here, and we develop different submarine type features on the ocean floor. So tides, we want to talk about what are tides. You probably heard about the tidal forces and when low and high tide occurs. And essentially tides are form as a result of the moon's gravitational pull on the earth. And we have there's 2 tidal cycles per day, and they range anywhere from a few centimeters to 15 meters. And here it's just showing you kind of the phases of the moon and what happens. And I guess this bluer part is defined as the tidal bulge. And again, there's going to be 2 tidal bulges, one on this side, and then there's going to be a bulge on the opposite side of the Earth. And typically, the larger bulge in this situation here is going to be towards the moon. So, how do these affect? How does these affect the Earth? And here's an example here in Duke Inlet in Alaska, where we have a low tide, obviously, and it's of a 10-meter tidal range here. And for instance, here's that same exact photograph at a high tide, and it's been completely submerged due to this tidal generating force. So how can we use these tidal generating forces, I guess, for more of a positive kind of effect? And here in France, they've used these, they call them an estuary tidal power generating plant, where they essentially harness this tidal basically change, and they create electricity from this. And they've kind of got a sequence here in the diagram going A through D here, showing here during high tide, they're going to basically harness this water, and it's going to basically go through this concrete dam and turn this turbine, and then it's going to create electricity. Here B, it's showing where it's in equilibrium. Here on the other hand, at C, water is flowing from the other side during low tide, and then it's balanced out at the end here in D. So this is just another means of kind of an ingenious way to utilize the tide. So waves. I'm going to briefly just talk about some of the features of waves and how they form. So here are the components of the waves, where we have the crest, which is located here, which is the top of the wave, and then we have the trough, which is going to be the lower part of the wave, and then we have the wavelength, which is basically the distance between 2 crests or troughs in a wave. And then the wave height is going to be basically the height from the top of the crest to the bottom of the trough. And then there's a period also, which is the time interval between the arrival of the two crests. And again, how do waves form? Essentially, waves form due to the shear force of the wind along the ocean surface. And as you can see here, basically this is the orbital path of the wave. And you can see at the top surface of the wave, it's more circular. And as you decrease or go deeper in the water column, that the diameter of that circle is going to change. And right at this point here, below here, I guess when the diameter of that circle, when it approaches half the wavelength, that's when we're going to get no more wave action, and that's actually below this dotted line. So you probably remember maybe in movies, submarine movies, all of the subs are going to be below wave base, and that's because there's no shifting or changing in the water dynamics, and it's really smooth. So submarines are always going to be flowing below wave base. So I thought that's interesting, to me at least. So here's kind of this another kind of cross section of a wave and the beach line, showing different components and features of different waves. So in this case, they're talking about basically a short wavelength is going to have a higher frequency, and it's showing here basically this breaking wave gains much height at the point where it approaches the beach shoreline. You're going to have a very weak swash, but then as the wave crashes towards the beach, it's going to kind of be sucked back, and that's the backwash, or that's where you have your very dangerous rip current. But also, I want you guys to note that here your wave is going to have more of a circular orbit, and as the wave approaches the shoreline, it's going to become basically more elliptical, and that's due basically to the morphology of the wave, and the friction that slows the wave at the base of the wave at the bottom of the shore line. It's gonna so that's why it's created there. So I think at this point I'm gonna stop at this point, and we'll resume at a later period here. I'm just trying to close this out. Let me try here. Sorry about this. It appears that my